can be invertible, non-invertible, something like this. But we will not be classifying our system. We will be using this classification to further characterize our system. But one assumption is that we are assuming that now our system is LTI. So we will not be defining our LTI and the related issues again. Our system is linear and it is time variant, we are assuming. Then after having this thing assumed, we will be relating the other properties of the system gradually with the equations that we have used earlier. Those equations are actually discrete time convolution sum and continuous time convolution integral. So your convolution process is actually related to finding the output of an LTI if for an arbitrary input, if the impulse response is known to us. Impulse response actually characterizing the whole system. As we have discussed in our earlier classes, that in your control system, you are dealing with what you call transfer function. Your transfer function is the input-output relationship of a system if your input is an impulse. The Laplace inverse of transfer functions is actually the impulse response. So when we model a system, then whatever they are inside our system, depending on the location of the input and the output, you have to derive the input-output relationship from where we derive the transfer function. So all the characteristic of our system is actually transferred into the impulse response of our system. As a result, impulse response will determine the properties of your system. For example, if we have a memoryless type LTI system, then we have to examine that what will be the nature of your impulse response for memoryless system. Memoryless system means what? The system whose input depends on the present value of your input depends on the present value of the input because it cannot memorize anything. So if this is the case, then we have to identify that what would be the nature of the transfer function, the impulse response for our memoryless type system. One such examples of our memoryless system is a register. Okay, if we consider that your register is ideal and linear, then you when you apply a voltage to the resistor, it will give you an output. When you withdraw the voltage, do you get any output?
No, sir.
No problem. Okay. So this is our memoryless type. Okay. So now, what will be the nature of H for your memoryless system? Okay. Can you see this? Okay. Please do not make your camera on. If you make camera on, then this window will be cluttered with many images. Okay. So can you see equation 2.2?
Yes, sir.
Okay.
Yes, sir.
What is it actually? You see that it is the expansion of this convolution sum. You know that convolution is actually has the commutative property. Commutative property means the position of h and x can be swapped. That means this equation is equal to xn convolution hn. If we write the thing if we expand this sum, starting from say k equal to -2, then it is h minus 2 x n plus 2. Can you tell me that where this signal or where this is located? For example, for n equal to, if we put n equal to 0 there in this equation, n equal to 0, then what you will get? H minus 2 into x2, isn't it? This term for n equal to 0.
Yes, sir.
Okay. So where it is located, if you want to just draw the time scale, you will see that this is your n equal to 0. These are the positive values of n. This region is for negative. So negative values of n are actually the past, what do you call, the past values, and positive values are n are the future values, and n equal to 0 is the present value. So for n equal to 0, if we want to calculate the y0, That means we are calculating this value at present. Then in that case, you will see that this term h minus 2 into x2 will be there, but x2 is yet to come. That's why you will not get that output. Similarly, x plus 1, you will not get output. For h0, we will only have output for this signal, but this output will also be 0. So what you can say, that your Sk will be 0 for k is not equal to 0, because it depends on the present values only, not for the past values and the future one. So what will happen then? Only this term will present in your output, h0 into xn. And you know that h0 is a sample. If it is a sample and all h's are there, all are actually sample values. So if h is a sample, it will have a magnitude, and it is located at n equal to k equal to 0. So it is a discrete impulse. Then the value of h0 can be something like this, okay, at k equal to 0. So we can easily express it in terms of delta function at k equal to 0. This is this. So you see the amplitude present there, okay. It depends on the real system, what will be the thing, okay. And you see that this behavior is very similar to some proportional type behavior. Okay, just wait a bit, somebody is calling me repeatedly. Okay. So it will take the shape of an impulse. Similar thing will be there for the case of continuous time case. It will also be an scale value of impulse. So you have to remember that for a memory-less type system, no matter whether it is continuous or discrete, the impulse response will take the form of an impulse. Now we have our causal system. Causal systems are defined earlier that the output value of the system depends on the present and past values of the input, but it will not depend on the future values of the input. Okay, so if we just examine the same equation that we have examined earlier, this is this equation. What we have seen that the xn minus 1, xn minus 2 are the past values of your input. Xn is the present, and all other the past value that can be identified by putting the value of n. Okay, you put the value of n, you will see that for n equal to 0, it is x n minus, because it is your comparison should be made from the present position. Okay, with respect to the present position where your xn minus 1, xn minus 2 are located. In this way, we can see that these are the past samples are also associated with k is greater than equal to 0, and the impulse response of Hk, while future values of the output are associated with n plus 1 and xn plus 2 for k is less than equal to 0. So as you know that your system will not deal with future values, then what will happen? H values for k is less than equal to 0 will be equal to 0. So as a result, what will happen? You will be summing your thing in your convolution sum from k equal to 0 to infinity. And your integral will be from 0 to infinity for continuous case and for discrete case. Most of the system are real-time systems are of causal type. Now stable and unstable system. Okay,
The previous one, Sir, the causal system is only dependent on the previous and the present value, right?
Not previous, yes, past and present value, yeah.
So, sir, shouldn't it be from minus infinity to 0?
Why?
Because it's taking the past values
Past value, how to identify the past value?
from the reference.
From the reference. So if you start with from the reference, you see that your x, okay, we have two things, say xn minus 1, xn minus 1 and xn plus 1. Which one is past?
Sir, in minus 1 is the past value.
Yeah. So if x minus 1 is the past value, you see that your x minus 1 associated with the positive values of k for h. And
Yes, sir.
this one is related to negative values of case, okay? So if this output is not available, then your input cannot be made 0 because your input is there. But then your impulse response of the system will not take, for example, will not have the value sk for k is less than 0, okay?
Okay, sir.
You understand?
Yes, sir.
Okay, that's good. Now, stability and instability, I hope you can intuitively understand it. Stable means what? Because our independent variable is time. In terms of digital case, it is sample number. In continuous case, it is time. Okay. In either cases, you see, if your number of sample is increasing, n is increasing, then if any one of the quantities that is increasing indefinitely with n or time, then can we expect that we will get the value, for example, that is in many of the cases you cannot get the value that is what you call bounded in time. Okay, we can just examine the thing by our earlier understanding. Okay, consider that we have, for example, in the last class probably we evaluated this convolution. Okay, say this is your h, st. If this is our st and we have a reflected value of a pulse, something like this, okay, say this is your xt minus tau, okay, and your duration is 1 minus 1. That means originally your pulse was something like this, 0 to 1. This is your input xt. Then we reflected it and put it here, and our impulse response is unit step. Okay, we know that your output will be equal to what? Xt convolution st, isn't it? Can you tell me that what will be the output if you want to plot the output, how it will look like? Your output will gradually increase and remaining constant, isn't it? You understand the thing?
No, sir. Can you repeat it again, sir?
You did not you see this example in the last day that if we have an input something like this, we have our impulse response something like this. Then this convolution operation can be graphically started with this figure, isn't it?
Yes, sir.
Then if we if we move our t, for example, in this side, there will be no overlap, isn't it? Your overlap begins at t equal to 0, and it is going in this region way. Okay, say your t is increasing in the positive side. When a complete overlap is occurring, will the output change?
No, sir.
As a result, you see that your output will be gradually increasing and remaining constant, something like this, isn't it?
Yes, sir.
Yes, sir.
So you see that here your impulse response is not bounded, but your this is correct. This is correct. Yes. Okay. Can you verify it? Because this end will be equal to t, this end will be equal to minus 1 plus t, isn't it? So if we integrate it, for example, both pulse has the amplitude 1 into 1, your integration will start from -1 plus t2 t dt, isn't it? And
Yes,
that is
sir.
equal to what? T minus plus
Minus
1 minus t, isn't it?
yes,
So
sir.
it will be equal to 1, okay? So and that the value will be remaining same for no matter where you integrate it, if you are going from t is greater than 1, isn't it?
Yes, sir.
If we calculate this integral for t is greater than 1, this value will be equal to always 1. Now consider that this input is now a step or something like this, okay? It is also instead of your pulse, it is a step. What will happen?
The
So,
value will divert.
so it will continuously increase.
It will continuously increase, okay? What we have seen earlier that if we have our 2 unit steps there, if you convolute them, it will generate a RAM, isn't it?
Yes, sir.
Your RAM signal is bounded in time or unbounded in time?
So unbounded.
Okay, then if we have this type of input in a stable system, will you get any finite output? Your output will be infinite, isn't it?
Yes,
That means
sir.
system will be
Yes,
growing
sir.
unstable. So in order to study the instability, then what you need to do, we have to examine the magnitude of our input as well as the magnitude of our impulse response, isn't it? If this is your magnitude, then this is equivalently magnitude of this quantity. Then this whole magnitude will again be depending on what? Magnitude of S and magnitude of Xn minus K individually. If any one of these things will can make your system unstable. So in the case of instability, what you need to do, the condition is what? The mx, okay, the magnitude parameter of x should be within this limit. Okay, it should be finite, and your h y, then y, that means a bounded input will give you a bounded output.
So the right condition is shouldn't it be less than only, not less than equal?
Which condition?
So the infinite condition, mx
M
less
will
than.
be less than equal to infinity. If it is greater than, then it will be unstable. There,
No, sir. So
unbounded.
I'm telling that how can something be equal to infinite?
How can something be infinite?
Sir, shouldn't it be just less than infinite?
It is less than or less than equal to infinite. Oh, okay. It should be less than infinity.
Yes,
Okay,
sir.
okay. It may be less than infinity, no problem. So in this way, you can proceed with. Then some examples are there. Try to redo it. You will understand the thing. Okay. One important issue is this regarding your age. Okay, if your age is growing, for example, if we have our age, that age will determine the nature of your system. Okay, that means if you conclude that the impulse response of a stable system, discrete time should have this inequality satisfied, and you for your continuous time case, this integral should be there, otherwise your system will be unstable. Then if the impulse response is given, then from that impulse response you can test that whether this sum or this integral is satisfied or not. Okay, so with this thing you can easily examine that your ST, for example, if we have our ST in this signal is finite duration signal, isn't it?
Yes, sir.
Yes, sir.
It is a pulse, isn't it? If it is a pulse, and we know that for our, okay, this is your ST, isn't it? Even if you change the value of T to tau, it will be S tau. So you see that some minus values of your H minus values of tau is actually a non-causal type. So if a minus value will exist, then your signal will not be causal. So it is non-causal. Now the thing is that whether it is stable or not, is it stable?
Yes, sir.
What is the test actually? You know that the test is you have to integrate, for example, H tau magnitude, H tau d tau should be less than infinity, isn't it?
Yes, sir.
Okay, in the previous network connection is going down. Okay, then this is actually finite. How about your second exam problem? This one.
So it's an unbounded system
Why?
because
Because there will be a negative portion of the signal that will run till infinity.
From t equal to 1 to infinity. Very good. So you know this thing. So try to investigate the other, please. Okay. We will again apply this thing somewhere in more general. This is actually very general description about the stability. Similarly, we have our system that can be a what type of system? That can be invertible, and from that invertibility of the system, we can define a quantity called deconvolution. Actually, deconvolution means the inverse of your convolution. Okay. This type of operation is needed in many of our practical purposes. Consider that we have a system. Okay, let me use whiteboard. Okay, then it will be easier for you. And the description is there. You can read it. You will understand it if you understand the mechanism. In our chapter 1, we studied this thing a bit in a simpler way, that if we have a, for example, system, that system is taking an input xt, and say this system has an impulse response ht, we are getting an output yt, Now, if this yt is given as the input of another system, we are putting an I there as superscript, just to differentiate the impulse response of these two systems. Then we are getting the system back, input back. We name this system as invertible, isn't it?
Yes, sir.
In terms of operator, we have seen that H into H inverse operator give you an identity operator, isn't it?
Yes, sir.
It is it give you an identity operator. So if you want to just proceed with convolution, because here the operation was not clearly mentioned. So if we just start with our convolution operation that we have learned, then your yt equal to what? Your yt would be equal to xt convolution what? ht, isn't it?
yes, sir.
Yes, sir.
Okay, now if we go to the second system, then your yt convolution hit is equal to xt, isn't it?
Yes, sir.
And we know that when two systems, is it not a cascade type system?
Yes, sir.
If we have a
Yes, sir.
cascade system, then that system can now be again written as in this way, okay? Then you will have an overall, for example, H impulse response of this system, isn't it? How that impulse response can be determined? It can be determined by the convolution of the individual subsystem impulse responses, isn't it? And that you can easily identify if we replace, for example, y, then this xt would be equal to what? We know that y is equal to xt convolution ht, isn't it? Now again it is being convoluted by HIT, isn't it?
Yes, sir.
Okay. Then you can group, for example, these two as this. Associative property of convolution. Okay. Then can you tell me from your earlier learning that what will be the value of this thing? What we are getting, that we are getting our input back, isn't it, at the output?
Yes, sir. So we're basically
So
multiplying by
multiplication operation is, we are not, for example, dealing with any multiplication operation, okay? Because we are dealing with convolution. In time domain, input-output relationship cannot be, for example, determined by simple multiplication. It must be convolution operation with impulse response. So we are just having this thing with us. And you can easily say that convolution of a delta function with a function is equal to that function, isn't it?
Sir.
Sir.
So then what conclusion can be drawn then? That if we have an invertible system that has the forward system has the impulse response ST and the inverse system has the impulse response HIT, if we convolute them, it must be equal to delta T, okay? Only when you will get your output back from the input back from the output. Actually, in the last night, I could not sleep. So it became very tiresome job for me now to continue 2 consecutive lectures. Okay, and that is true for discrete time signals also. Okay, all the system properties are summarized in this table. Now we will be going to a topic that is very important for you in terms of system engineering, and I hope that you have already have some experience of using this term in your control engineering. Have you heard about step response in your control engineering? Not yet?
Sir, the input is a step function.
Of course, a step function, but I am referring the problem that whether you have learned this thing in your control or not. Not yet.
not in details, but we learned about its Laplace.
In Laplace, okay, yes. In Laplace, you learned about it, okay. So I will again be going to a whiteboard just to discuss these issues of step response and impulse response. How can you commute between them, okay? And I will just ask that you please try to understand the thing very carefully. The reason is that it will be needed in your control engineering also, okay? Because these are the standard, what you call, input to characterize the nature of your system. Actually, you see that what is there in impulse response of your system, okay? What you have learned, just you know that if we have a system, that system should be translated into mathematical model, isn't it? So in your mathematical model, you will have some equations, isn't it? Again, those equations can be transferred into some quantities that we usually call transfer function. And you know this term transfer function from your control probably, okay? You know it.
Yes.
sir.
A transfer function is actually particularly used in transform domain. Transform domain, okay? You have two transform domain, okay? We use Laplace transform, or sometimes we use Fourier transform, okay? Both are Laplace domain, yeah, transform domain. Okay, how this transformation is done? You see that we illustrated it in the case of an RC circuit in the last class. That if we have an input or output, for example, a system, something like this, then in the Laplace transform, we can easily transfer this circuit into this form. Then you can apply your resistive potential divide rule to calculate your Ys, if Y is the voltage across this capacitor. Then what we have seen that the ratio of your input divided by ratio of your output Ys divided by input was a transfer function, something like this, RCS plus 1. Okay, this quantity we call it equal ACS, the transfer function, isn't it? Just I am rewriting the thing just to let you know that how transfer function, how the system parameters are transferred to transfer function. Okay, you see that in your system, your voltage input and outputs are there in one side, but in your ACS, in our circuit, we have our element values R and C. Other than ACS, is there any thing available here where R and C are involved? XS or YS এর মধ্যে কি RCS আছে? Is there any RCS in XS and YS?
No, sir.
What does it mean then? That means your ACS actually contains all the system parameters. That means system element values or all other things will be there in your ACS. So if we can, and that ACS is not something like that meaningless, okay? This ACS is actually the ACS, if your XS is equal to 1, then your YS is equal to ACS. Is it not the impulse response of your system in Laplace transform?
Yes, sir.
So your ACS, although we call it transfer function, but it is also the response impulse response in transform domain. If we take inverse, then inverse of Laplace transform will give you the impulse response that we usually call time domain impulse response. But customarily we do not use, for example, impulse response in transfer domain for ACS. We call it simply the transfer function. This transfer function will tell you how your input is transformed to the output, okay? And how, okay, for example, say, we know that our S is equal to sigma plus j omega. It is called complex frequency. If we want to convert it into Fourier transform, this quantity would be equal to Hj omega. And in this RC circuit, your Hj omega would be equal to 1 divided by RC j omega plus 1, isn't it? Because your S equal to j omega.
Yes, sir.
Then what is the magnitude of this thing? The magnitude of this thing, it is simply equal to square root of R square C square plus omega R square C square omega square plus 1, isn't it?
Yes, sir.
Can you plot it? What is the value of this transfer function at omega equal to 0?
The 1.
1. Then what will be the value at omega equal to infinity?
There's 0.
0.
So how is it changing? Actually, it is changing hyperbolically, something like this, isn't it?
Yes.
This is the magnitude of our Hj omega. So this is what the frequency response of your RC circuit. That means you can say that up to this frequency, up to certain frequency, you will have significant output. And beyond that frequency, you will have no output, or output will be very, very small. Then if your transfer function has this type of nature, what type of operation is being performed by this circuit?
Filtration.
What type of filter?
Low pass filter.
It is a simple low pass filter, isn't it?
Sir, passive low pass filter.
Okay, it is a simple passive low pass filter. Okay, ideal. And whenever student starts learning filter, they start from this example. Okay, this is a very nice example how your filtering operation is done, and that can physically be understood that if we have a capacitor, and because that filtering operation, this transfer function is related to what? You are taking voltage across the capacitor, not other cases. So you see that voltage across capacitor depending on the impedance of this capacitor, and you know that the impedance of this capacitor is inversely proportional to C, isn't it?
Yes, sir.
That at very high frequency, what is your impedance? Is it not equal to 0? That means your capacitor will be infinite. Your capacitor will be behaving like a what? Short circuit at very high frequencies. Okay, as a result, no output will be available. But at DC, in steady state case, it will be behaving like open circuit, so that you will be getting your most of the voltage at your output. Okay, so in this way, your transfer function and impulse response are related to the system behavior. Now, not only the impulse response, because you see that by examining the Hs or Hj omega, you can have a fair idea about the operation of the system. For this reason, our impulse response or transfer functions are very, very important. Okay, before going to the time domain response, by examining the nature of your transfer function, we can identify whether we will be getting our desired output or not. Now, in addition to the impulse response, we use another response there, input there, that is called a step response. A step response means, in our earlier case, our input was, okay, we are referring continuous time only, but this is equally applicable for discrete cases, okay, where integral will be replaced by sum. So input is this for impulse response. Now our input will be equal to what? For a step response?
UT.
UT, yes. If we have this input with us, okay, either you can use the integral equation that we are using to find the output, or you can use your transform technique, that because all are the mathematical techniques, you know the mathematics, you can proceed with doing this thing using mathematics also. So if I want to use, for example, we know that the input output relationship of our system is something like this in Laplace transform, Ys divided by Xs is equal to what? Hs, isn't it?
Yes, sir.
Our objective is we need to find our Yt if our input is a
UT.
unit step, UTS. In this case, when we take Laplace transform Xs, it was equal to 1, isn't it?
Yes, sir.
If we take the Laplace inverse of unit step for the latter case, it will be equal to what?
1 by S.
1 by S. Very good. So if it is 1 by S, then you put this value of S there. Then your output Ys equal to what? Xs multiplied by Hs. Your Xs is equal to 1 by S. Isn't it?
Yes, sir.
Now you have to invert it. Okay. Assume that you have already this Hs is available to you. Okay, this is available. That means our Hs is known to us, or equivalently Ht is also known to us. Okay.
Yes, sir.
Now we have to find, say, Yss step response. In the Laplace transform, we obtain this thing. Okay, now I am asking a question to you. For example, if we have our function fs whose Laplace transform inverse is ft, Then if we multiply this function by 1 by s fs, what will be the Laplace inverse? Because in Laplace transform, we have differential and integral properties of Laplace transform. Or tell me, what is the Laplace transform of, say, integration ft dt?
Fs. Oh no, sir.
Is it fs?
Fs by s.
Fs by s, okay. If initial values are 0. If initial values are 0, then it is fs by s. Then in that case, your ys would be equal to what? Yt inverse would be equal to a simple integration of what? Integration of st dt, isn't it?
Yes, sir.
So in this way, you can commute between your impulse response to what you call step response, okay? And integration limit should be set accordingly. Now, if we want to go back, for example, ys is known to you, we want to find, for example, st. How can we do that? If we differentiate our yst by dt, you will get your impulse response from your step response, okay? So in this way, you can proceed. Okay, that can be understood from Laplace transform also. You see that in our Laplace transform forward case, we obtain YSS, the step response is equal to 1 by S HS. Now, if you want to find HS is equal to what? S into YSS, isn't it?
Yes, sir.
Then if a function is multiplied by S, then it Laplace transform, is it not the derivative?
Yes, sir.
So then your ST would be equal to what? ST would be equal to derivative of
Ys. Yt.
YST. In your book, probably YST is represented by ST, okay, step response. So in this way, we can find our step response from impulse response from step response, okay? Because step response is also important in order to understand the transient behavior of our system, okay? You will learn in depth about it when you will be going to your system or response categorization in control system. Okay, we need to implement it for our the same thing for our discrete time case, okay? We can easily find that for our discrete time case, if your Sn is the step response, your Sn will be equal to sum of Hn, okay? And in the same way, if you want to go, if your Sn is known, we can find your Hn, you know, just like differentiation, okay? You know that in the discrete time case, our independent variable is n. The distance between two successive n is equal to 1. As a result, what you can do, if we just make a difference of two successive samples, then you will get your
Derivative.
derivative, okay? And that will be your impulse response. Okay, all these things are described here. The summarized, okay, for your discrete time case, this is what the relationship this is how you can obtain your step response from impulse response. And by using integral, you can use for you this integral for your continuous time system. An example is there. Okay, in our last example, we for RC circuit, we determined that the impulse response of your RC circuit is equal to what? 1 divided by RC e to the power minus t by RC ut. We found it earlier. Or it is simple Laplace inverse of RCS plus 1, isn't it? Your ACS is equal to what? Your ACS is equal to 1 by RCS plus 1, isn't it? And
Yes.
you can write this equation in this way: 1 divided by RC into 1 divided by 1 plus 1 S plus 1 divided by RC. Can you write it?
Yes, sir.
Then your ST would be equal to what? ST equal to 1 by RC e to the power minus T divided by RC, and UT should be there as it is from time t equal to 0 to infinity. So this is your ST UT. Then if we integrate it, and you will see that that integration will be giving you this value, and you will surprisingly see that this is what you have already learned in your first year. Okay. And okay, for your step response, can you remember what is the output for an RC circuit? For an RC circuit, your step response is equal to what? Is it not
1 by RC plus 1.
It is simply equal to what? 1 into 1 minus e to the power minus T by RC, isn't it? UT. That means your output will be 0 at time t equal to 0, gradually going and settle down to a value equal to 1,
1.
isn't it? And
Yes,
how
sir.
fast or how slow it will be going, it depends on the time constant RC. If this is the case, okay, you see that if we integrate our impulse response, you see, and that impulse response will give you the same equation. And you can identify this equation there. Is it not that equation that we plotted earlier? That equation can be written as 1 minus e to the power minus T by RC UT, isn't it?
Yes, sir.
For ut is less than 0, value 0. For t is greater than equal to 1, value will be equal to this. Okay. And if you plot this, it will take this shape. So in this way, you can calculate your step response from impulse response. If you, and you differentiate it, can you go back there?
Yes, sir.
So some examples are there, practice problems are there. You practice, please. I want to finish my lecture today at this point because I am a bit tired. We will move from this point ahead in the next class, inshallah. Okay.